So far, we have studied unsigned numbers. So we were unable to represent the negative values. So let's study how the computer represents the negative value. So there are several ways of doing so, but in common or not in common, is most popular way of doing so is reserve a bit, usually the high order bit, the leftmost one, or called the most significant position. Use that bit as a sign. So if you have several bits there, then the leftmost one is reserved as a sign. If it's a zero, positive, one negative. That's the most popular way of doing so. But there is another mechanism not doing this way though. But anyway, let's study how we can represent negative numbers. So there are basically three ways using the leftmost bit as a sign. So sign the magnitude, one's complement, and the two's complement are there. So if we use 8-bit number, then only 7 bits are used to represent the value, and then the leftmost 1 bit is a sign, positive or negative. So here is an example. In 8-bit number system, let's assume that then this value, except the leftmost bit, this value is a 3. Since the leftmost bit is a 0, we consider it as a positive 3. Similarly, this value is a 3, but the leftmost bit is a 1. We consider this one as a negative 1. So this idea is most straightforward. That's the way humans carry out those arithmetic and representation in decimal numbers. So this is exactly the same way we want to represent the negative values in binary in computing system. However, this assigned magnitude representation is easy for people, but it is complicated for computer hardware. So this one is not actually used in computer. So another disadvantage of assigned magnitude representation is we have two different representation of 0, positive 0 or negative 0. So in 8-bit, so in 7 bits are 0, then the value is 0. Then you can have a positive 0 or negative 0. So it's a positive 0, negative 0. So differentiating those two zeros are meaningless. So that's another disadvantage when you use a signed magnitude representation. So in this reason, in actual computing system, we use a complement system. So complement system, we have two ways of doing so. The first one is called diminished radix complement. In other words, in binary system, this is known as a ones complement, but generalization is called a diminished radix complement. It's defined as follows. For a number n, in the base r, this is radix, so binary, this is 2, and then number of digits there, then negative n is represented by this formula. So let's do this one for binary. So suppose we have a 4-bit number, then d is a 4, so digits d is a 4. Then suppose n is a 3, so we have a 3. Then how do we represent the negative 3? And then r is in binary system is a 2. So negative 3 is represented by this formula that base is a radix is 2, number of bits is a 4, minus 1, minus n is a negative 3. So this is a 16, so 15. So 15 minus 3 is a 12. So in 4-bit system, 12 is represented as negative 3. So 12 means in 4-bit, it's a 1100 is a 12 in 4-bit. So 3 is a 0011 is a 3. This is a 3, and this is a negative 3 in 4-bit ones complement system. So in binary, diminished radix in binary is called the ones complement. So in ones complement, it's simply flipping each bit is ones complement. So anyway, in this ones complement representation, the leftmost bit is used as a sign. 0 means positive, 1 means negative, and the rest, unlike assigned magnitude, you don't see the value directly why you have a negative 3. But positive ones, you see the positive 3 immediately. But ones complement, this part, except the sign, the value part is a kind of encrypted by this formula. But ones complement, we know that we can get by flipping the bits. So what I mean by this follows. In 4-bit, so how do we represent the negative 5 then? Then positive 5 is 0, 1, 0, 1 is a positive 5. Then negative 5 is simply flipping those bits. So 1, 0, 1, 0, this is a negative 5. That's a ones complement representation. So here is another example. Suppose we have 8-bit, then how do we represent ones complement? So positive 3, this is a positive 3 ones complement system. The negative 3 in ones complement is simply flip each bit. Then what you get is a ones complement. Actually, this result is by the formula. So the formula is n is a 3. We want to find the negative 3. Then our base is binary 2, and then 8 bits minus 1 minus n is the formula for negative 3. So if this is a 3, then 2 to the 8th power is 256. So minus 1 is 255. So minus 3 is 252 is the value. So if you convert this binary number into decimal value, you will find it's 252. So that's a ones complement representation. This complementary system is useful, but in computing system, we do not use a ones complement. Actually, we use a twos complement. That's in next video lesson. But one of the disadvantage of a ones complement is, again, you have 2 zeros. So all zeros in 8-bit is 0. We know that. But if we invert it, it's all ones, which is also 0, negative 0, positive 0. So like assigned magnitude representation, ones complement also has 2 zeros, and then that's not efficient. So in modern computers, ones complement is not used, but twos complement is used. That's the subject of next study.